Welcome to the deep dive. Something we've definitely been noticing, particularly from our time teaching information security, is this feeling. Well, it feels like the actual art of proving security is maybe getting a bit lost.
It really is an interesting observation. I mean, on the one hand, we've seen cybersecurity awareness shoot up in businesses.
Yeah.
Like the CISO role is much more common now.
Definitely positive steps.
Yeah. And standardization has helped make security services more widely consumed, and the demand for training is huge. So, lots of good things happening.
Absolutely. Can't argue with more awareness and training. But then you look at some other trends and you start to wonder if we're losing something fundamental.
That's exactly it. Like one thing we've seen is how tricky it can be to actually verify security qualifications.
Yeah.
Especially, say, for folks coming from different regions trying to work in the US or Europe. It's hard to compare apples to apples,
Right.
skill-wise.
And it's not just about global differences, is it? Even with all these security products becoming more, well, consumerized, you worry about quality. Are people just buying a box without really understanding if it solves their specific problem?
That's a great point. It can feel like that sometimes.
Yeah.
And maybe the biggest worry is that the really deep foundational expertise might be thinning out. There's such a focus on just following the standards, ticking the boxes for compliance.
Which lands us right at what feels like the core problem. Security teams sometimes seem to be just, mindlessly following standards without actually proving their systems are secure. It's compliance over actual demonstrable security.
Right. Saying you're secure versus showing it. So for this deep dive, we really wanted to get into what a proof-based approach looks like for creating secure automated systems. Think of it as us, kind of like instructors, walking through how you build that proof.
Exactly. And to do that, we've got some source material we're going to unpack. We'll look at a specific way of handling data in an organization, then the security policy meant to protect it, and finally, we'll dive into a formal model of an automated system. The idea is to tie it all together so we can actually talk about proof.
Okay, so let's start with the first piece, the technology for working with data. Imagine an organization, right? Multiple departments, interconnected, different jobs to do.
Standard stuff, sales, engineering, whatever. They have their own tasks but need to collaborate.
Precisely. And to make that collaboration work, their tasks are automated using a shared database. Now, here's the interesting bit from the material. The content isn't necessarily secret, but its availability is absolutely critical.
Ah, okay. So it's not top secret data, but if that database goes down.
Exactly. If it's down, the department grinds to a halt, the whole organization feels it. It causes real damage because it's central to their workflow.
Got it. Availability is king for this shared database. But people must handle sensitive stuff too, right?
They do. Alongside that database, employees work with confidential information in documents. And these need tight security. If these documents leak, that could really harm the organization. Sensitive client data, strategic plans, that sort of thing.
Okay, so two tiers. The highly available, maybe less sensitive database, and then these confidential documents needing stricter control.
Correct. And the source describes a pretty standard setup for handling these documents. Employees create them, maybe print them, on their workstations called ARMs, automated workstations, all linked on a local network, the LAN.
So typical office computers networked together.
Yep. And they're using multitasking operating systems, meaning you can run several programs at once. Document data lives in files, processed by various OS programs.
Right, the multitasking adds complexity potentially. Different apps touching the same data, maybe.
That's a good point. And the source emphasizes that this whole setup, the workstations, the LAN gear, the server, the network OS tools, it all works together to support this data handling. It's one big interconnected system.
Okay, picture established. Network departments, critical shared database, sensitive local documents, standard tech infrastructure. So how do they try to secure this? That takes us to the security policy, I guess.
Exactly. The next layer is this selective security policy, tailored for the tech we just described. First rule, documents and databases are valuable assets. Simple enough, but it means access must be controlled.
And how do they control it? Just file permissions?
It's meant to be broader than that. The policy calls for a mix. Organizational measures like defining roles, technical measures like system settings, security software, and specific security tools like access control lists, maybe encryption, a multi-layered approach.
Right, not just tech, but process and people too. What else?
Second point, the system is considered closed. Only authorized people inside the organization should access documents and the database. Now, a truly closed system today is tricky, but the principle is clear. limit access to a defined, trusted group.
Makes sense for valuable data. Keep it internal. What about the admin, the person with the keys to the kingdom?
Good question. Rule 3 addresses that directly. Management, acting through the system administrator, gets access to all documents and databases. It acknowledges you need that central control point.
Okay, so the admin is the super user. Big responsibility there. How does the policy handle access for regular employees then?
Rule 4 says management, again via the admin, defines the specific access rights for each employee to documents and databases. It's not one size fits all.
Tailored permissions based on job role, presumably.
Exactly. And Rule 5 gives the general guideline. Employees get access to stuff they create themselves. Plus, they get access to objects designated for collective use by their specific user group, think shared team folders or database areas.
Principle of least privilege, kind of. Access your own work and your team's shared stuff. What can't they access?
That's Rule 6, the final one here. It explicitly forbids a user accessing objects created by another user or objects belonging to a group they're not part of. Reinforces those boundaries.
Okay, summing up the policy. Assets are valuable, control access, system is closed, admin has full access, management defines user rights, users access their own stuff and their group stuff, no accessing other people's or other group stuff. Seems logical.
It does. And the source stresses that this policy and the mechanisms supporting it form a single, unified, secure environment. It's not just random rules.
And it has layers, right? It's not flat.
Right. A hierarchical architecture, top level.
Yeah.
The policy requirements themselves. Below that, the user interface.
Yeah.
Then multiple software protection layers, including OS stuff. And at the bottom, hardware security tools.
Defense in depth. Security at every level, policy down to hardware.
Precisely. And the crucial point the source makes. Every level below the policy, UI, software, hardware must implement the policy requirements through its protection mechanisms. The policy sets the goal. The tech has to achieve it.
Policy is the what, tech is the how, but the how can vary.
Absolutely. The exact way you implement access control might differ based on the OS or hardware. But, and this is key, however it's done, it must adequately reflect the policy requirements. The outcome enforcing the policy is what matters.
Okay, technology, policy. Now, how do we get rigorous? How do we move towards proving this policy holds? That's the model, isn't it?
That's the leap. To get to proof, we need a formal model of this automated system handling valuable info. The source starts by defining information objects. Think of these as the containers for valuable data documents, database records, maybe even program code, system files.
So object is just any digital thing we care about protecting.
Pretty much. Then the model uses discrete time steps like 1, 2, 3. It simplifies analyzing system changes state by state.
Why discrete time?
It makes modeling transitions easier than dealing with continuous flow. At any time, the system state is defined by the state of a finite set of these objects, always a limited number of objects.
Okay, so at any moment, a defined limited set of data containers. Who acts on them? That must be the subjects.
Exactly. At any time t, some objects are designated subjects. A subject is an object representing a transformation, an action. It gets a domain system resources it needs, like memory, and it's where control goes. Think of a running program. Needs resources, domain, executes code, process. So a subject is like a domain process pair.
Subjects are the active things, manipulating objects. Need resources, do tasks.
Right. And they have two states. Non-activated, just a description, or activated, has its domain, running. And crucially, only an activated subject can activate another subject. A chain reaction.
Makes sense. Controlled activation flow. What happens when one activates another?
The model uses a graph, GT at each time t. An arrow from S1 to S2 means active S1 can activate S2. The activation itself, S1 or S2, is the transfer of control.
A map of potential control flow. Where do the actual people, the users, fit in?
Users are a special subset of subjects. In the model, they never have incoming arrows in any graph chain, meaning they're always considered activated initially. They kick things off by activating other subjects, the start points.
Users are the entry points, triggering actions. What about user groups from the policy?
The model defines user groups, G, simply as subsets of users who share the same access rights to common objects, those objects of collective use.
Just a way to bundle users for permissions. How does the model show how subjects interact with objects, read, write, etc.?
Through access types, a finite set R, with examples like read, write, execute. For an activated subject S and an object O, row, is the set of specific access rights S has to O, so row is a subset of R. Maybe S can read and execute O, but not write it.
So O is the specific permission set. What's the difference between S directly accessing O versus doing it via a chain of actions?
Good distinction. Direct access is SO. Access on behalf of is SO. The star means it's a sequence of accesses over some time interval, say T plus. A user starts a process, which starts another, which finally accesses the object that accessed on behalf of the original user.
Important for tracing authorization back. The model also tracks objects accessed at time t.
Yes, DT is the set of all objects accessed at time t. We can also define DDU, objects accessed on behalf of user U at time t, and DTG, objects accessed by group G at time t.
So we track what's accessed and ultimately by whom, user, or group.
Precisely. Then D is defined as the intersection of DTUI for all users UI. D represents the common system objects, potentially accessible by everyone. The model says users can create and delete objects, not indeed their own stuff, essentially.
Makes sense. Manage your own workspace separate from core system stuff. What about group-specific shared objects?
That's DGG. It's the intersection of DTG for all users UI in group G. These are the objects specifically for collective use by that group.
The digital shared project folder, how does access actually start?
With a request. SO subject S requests access type S to object O.
Standard request model. What about creating new objects?
If a subject activated on behalf of user U needs to create an object, it calls a creation procedure. The new object gets a unique name and is considered owned by U. It becomes part of OTU. Similar process for group creation, becoming part of OTG.
Ownership tied to the creator, user, or group. Crucial for access control, linking back to the policy.
Absolutely. Lastly, the model includes the privileged user, UADM, the system administrator. Unique at any time T has full rights to all common system objects in D.
The admin again. Okay, how does this whole formal setup help enforce the policy we talked about way back? How do we connect the rules to this model?
Right, here's the payoff. The policy rules get translated. An access request, SO, is allowed if, first, there's an activation chain from some user U leading to S. So S is acting on behalf of U, written S0. And second, the target object O is either owned by that user U, OLO auto to U, or O is a shared object for group G, and user U is in that group, OEGG and UNG.
So you get access if you or your process own it, or it's shared with your group. Directly maps to the policy principles. What about prohibited access in the model?
Similar translation. Access US to object O is prohibited if either O is owned by a different user, UURI or IRA, URI, and IRIE or RO belongs to a group G's shared stuff, area of DTG, but the requesting user, UE, is not in that group, UAE. Again, mirrors the policy restrictions.
Okay, policy rules translated into formal model language. Now the big question. How do we prove that if certain things are true, this policy will be enforced? How do we get to demonstration?
Exactly. We built the model. Now let's show it's secure under certain conditions. The source says we start with some intuitive assumptions, basic properties we think a secure system should have.
Assumptions that feel right for security. Okay, what's assumption one?
Assumption one. If subject S gets activated at time T, there's a unique activated subject S that activated it. And at time 0, only users are active. This ensures a clear, single activation path for everything, starting only from users.
So traceable activations, no mysterious processes starting themselves, and that leads to lemma 1.
Yeah, lemma 1 follows directly. If S is active at time T, there's a unique user U on whose behalf S is ultimately acting. The proof uses that unique activation chain back to a user, assuming finite operation time.
Every active process traces back to one user. Accountability. What's assumption 2?
Assumption 2 is broad. The system's operation is just the sequence of subject sets accessing object sets at each time step T. It defines what constitutes system behavior in our model.
Defines the scope behavior is access events, leading to lemma 2.
Right. Lemma 2 says, for any time T, if an object exists but isn't a common system object, OOET, then there's a unique user U who created it, OATU. This comes from the initial state and the creation rules.
If it's not a shared system thing, it belongs to a specific user who made it. Reinforces ownership.
Exactly. Now remember the admin. Assumption 3 makes that formal. At every time T, there's a unique user UADM with all rights to the common system objects in D.
Locks down the admin's unique, powerful role over shared resources. What about information leaking through those shared objects?
Assumption 4 tackles that. If O is a common object in D, then different users accessing it, UEO, UG, OA, UUG, cannot create an information leak channel, regardless of their access rights. 1, 2. This is a big assumption, basically saying that design prevents side channels via shared resources. Very hard to guarantee in practice, maybe.
Wow, okay. Common objects must be built or managed so users can't secretly pass info through them. That's huge. What's the last assumption?
Assumption 5 limits what privileged subjects can do. If a subject S itself is a common object, STD, and it's activated on behalf of user UI, UIS, then if S gets access to some object O at time T, one of these must be true. O is also common, OEG. OAO is owned by UEO, OAOD, OET. OEO is shared by a group G that UE belongs to, OUDG, OR. The system just aborts the access. It stops privileged system components from grabbing just anything.
So even system processes are bound by ownership and group rules when accessing things, or they get stopped. Okay, with those 5 assumptions, Theorem 1.
Yes. Theorem 1 states, if assumptions 1 to 5 and the security policy rules in model form are met, then unauthorized access is impossible. The proof is usually by contradiction. Assume unauthorized access happens, then show it violates one of the assumptions or lemmas about activation chains or access rights.
Assume the bad thing happens, show it leads to a logical impossibility, therefore the bad thing can't happen. Classic proof structure.
Exactly. So we've shown these assumptions are necessary. Now, the source pivots to building the system.
Yeah.
How do we implement things? What lower-level services do we need to actually enforce the policy?
Right, from theory to practice. How do we build mechanisms that meet the policy? That brings us to conditions 1, 2, and 3.
Precisely. Condition 1 is about identification and authentication, it says. Whenever there's an access request, row SEO, the system must be able to figure out which user set, common set, EVI, DK, both S and O belong to. Before deciding anything, you need to know who's asking, what they're asking for, and their context within the ownership group structure. Of course, perfect INA is a real challenge.
Job 1. Know who's talking to what and where they fit in the security picture. What's condition 2?
Condition 2 is the authorization subsystem. It lays down the rules based on condition 1's info. If user U initiates action leading to S, UAS, and S requests access to O, SOO. If O belongs to U, access SO is allowed. But if O belongs to a different user, U, OA at TUJ, IAJ, access L or O is prohibited. Same logic for groups. If O is in DGG and user U is in group G, access is allowed. If U is not in group G, access is prohibited. This directly implements the policy's core rules.
Okay, this is the engine making the yes-no decisions based on ownership and group membership. Just like the policy said. Access your own stuff, your group stuff, nothing else. What's the final one? Condition 3.
Condition 3 is crucial. No bypass. It states, if a subject S successfully gets access SOO at time T, then there must have been a corresponding request, SO at that same time T. Prevents any access from happening without going through the formal request and authorization check. No sneaking around the side. Again, tricky to implement perfectly in complex systems.
Every access must have a matching, legitimate request. No shortcuts around the checks. These 3 conditions lead to Theorem 2.
They do. Theorem 2 proves sufficiency, it says. If conditions 1, 2, and 3 are met in the running system, the security policy is enforced. The proof shows that allowed policy accesses pass the conditions and prohibited policy accesses are blocked by the conditions, and the no bypass rule ensures everything goes through the checks.
So build the system to rigorously satisfy these 3 conditions, and you've effectively enforced the security policy.
That's the idea. So the final conclusion ties it all up. If the underlying assumptions 1 to 5 hold true, and if conditions 1 to 3 are properly implemented in the system, then unauthorized access is impossible. Both the foundational assumptions about behavior and the concrete implementation of these security conditions are vital for provable security. Real systems need solid mechanisms for both.
Wow. Okay, that was a really deep dive, really laying out the structure of how you'd even begin to prove security, rather than just assert it. It definitely highlights that real security is way more than just checklists. It needs this kind of rigorous, evidence-based foundation.
Absolutely. You can see how the technology choice, the security policy, and this formal model all have to work together, intricately connected, to get to a point where you can actually demonstrate security with some confidence, not just hope for it.
It really makes you think, doesn't it? With today's threats constantly changing, how can we apply these fundamental ideas of proving security? How do we, as people building and defending systems, move towards building things that are inherently more resilient because their security is based on evidence and proof, not just compliance? That's the challenge, isn't it? Something for all of us to think about. Thanks for joining us for this deep dive.